Okay, so in the last lecture, we had a few discussions regarding, general group theory. So we'll continue such discussions in this lecture as well. So I don't remember if we had discussed about cyclic groups or not. I guess we didn't, right? Yeah. So yeah, just let me just check once. Mm, we had discussed about order, right? Yeah, we had discussed about order of a group. We have a yeah. We did not discuss about cyclic groups. Correct. Okay, so let's start with it. Okay, so this is kind of the general group theory part 2. Okay, so the first thing we want to discuss today is the concept of a cyclic group. Cyclic. So, so basic thing is that suppose we have an element A, let's say, from a group G. Okay. Now what we are doing is we are continuously operating A on itself. So we have A, we call so we use the multiplicative operation on G only. So A times A, which is A squared, and we have A squared times A, which is A cubed, A to the power 4, and so on the process continues. And we consider A to the power 0, that is the identity element. Okay. So A to the A composed with A is A squared, A is A cubed, and so on. We will form a group of this type, and we add the identity, and we consider that to be the element A to the power 0. So this group, along with the multiplicative operation itself, is called the cyclic group. Okay, it's called the cyclic group, and this cyclic group is said to be generated by A. So that's the notation for saying generated by A. Okay. Now notice the fact that if suppose I say that this group is finite. So I mean to say that the group is finite. This group is finite. Okay. So now the first thing first, if this group is finite, then the first observation is that then after a certain point, the exponents should coincide, right? That is the only way possible for this set to be a finite set. So suppose a to the power r coincides with a to the power s. Clear? Then what can we say about them? So I can easily, write multiply with, a to the power as whole inverse. Other way of saying, so as whole inverse is nothing but as, a minus s, right? So, so this becomes a to the power r minus s equals to 1. Notice the fact that the multiplicative operation is analogous to the arithmetic of exponents, right? So it's a to the power r minus s, and r minus s is obviously a finite number because we have chosen r and s to be finite numbers, right? Because I just said that the elements must coincide after a certain point, and if it needs to be finite, then this process of being coinciding, that must happen after a finite number of terms. So r and s are both finite, and without loss of generality, let us assume r is greater than s. So that's a positive integer. So what does this mean? So if there exists some integer such that it's a to that power is 1, then obviously a has a finite order. So order of a is less than, and we can obviously say that this order of a divides r minus s, right? Because we have studied when we had studied the properties of order, that's pretty obvious from here. Because if you recall that if order of a is d, and we find that some a to the power n equal to 1, then that would imply d divides n, right? Converse is also true, correct? So that means now, so that basically means that if you choose any element from a group G and you form a set of this form, and you say that this set is finite, so this set is finite, then that means that A has a finite order. Clear? Now let's say suppose A has a finite order. So let the order of A be n. Let's say. Then, and obviously let's choose n be, let n be greater than equal to 1. N be arbitrary. So how can we list out the elements? So the first element can be is obviously 1 because we have assumed this to be a to the power 0. Then we can have A, and we can keep on composing A with itself, right? Until we reach the order, until we reach a to the power a. So we have 1 a squared, and so on till a to the power n minus 1, because as we cross this, then we get a to the power n, and that is same as 1, and we already have 1 listed in the set, right? And notice that if you consider a to the power n plus d, where let's say d is less than n and greater than equal to 1, then this is same as a to the power d, right? So that means if you exceed the power of n minus 1, then you get back the same elements, right? So that means the group generated by A is simply the set of elements 1 a squared, and so on till a to the power n minus 1. Clear? Clear? Okay. So so that means that if order of A is n, then that implies order of the cyclic group generated by A is again n, right? Okay. Now, now notice this. Let me write this a lemma itself. If A belongs to G and G has finite order, and G has finite order, then the order of A divides order of G. Okay. Now, why is it true? The first thing to notice here is that order of A will always be finite. Now, what is the reason behind that? Because if say order of A is infinite, then the cyclic group generated by A also has order infinite. That's pretty obvious, because you can keep on composing A with itself, unlimited, right? So if this happens, but since G is closed under its operation, so obviously every element in the cyclic group A is in G, right? So this must be contained in G. But this is infinite and this is finite. So that's obviously a contradiction. So order of A must always be finite, right? So we can talk about the division. Okay. So if I try to prove this statement, so the proof of this statement is pretty simple. So we have, so let A be in G. Consider H to be the cyclic group generated by A. Then H is obviously a subgroup of G, right? By the closure properties on G. So because see, since A is in G, so A to the power I is always in G for any times A is composed with itself. That is any exponent I, any integral exponent I. So obviously this cyclic group is inside G, and it's obviously in group under the same operation, right? So it's a subgroup of G. But that implies the order of H must divide order of G by the Lagrange's theorem, which we studied in the previous part. Now we had also proved that order of a cyclic group is the order of the element itself, right? But the element which generates the cyclic group. So that means order of A divides order of G. Yeah? Order of G in the sense the cardinality of the set G. So this is basically nothing but this. Yeah, correct. Okay? Pretty simple. Let's check the next important proposition. Let G be a group of prime order. Then G is cyclic. Okay. Let's check. So we are given G to be a group, right? So G is a group and order of G is prime. Let A be an element of G and A be the non-identity element of G, let's say. Okay, A is the non-identity element of G. Consider H to be the cyclic group generated by A. Now, this is pretty obvious that since A is not identity, therefore H is not the singleton set identity, and that is also a subgroup of G, right? G has two trivial subgroups. That is the identity subgroup and the whole group itself. Okay. So H is obviously not in. Now, by Lagrange's theorem, since H is a subgroup of G, so that implies H is a subgroup of G, right? Because H is chosen to be the cyclic group generated by A, where A is an element from G. So now by Lagrange's theorem, order of H must divide order of G. But order of G is a prime, right? So the order of H has only two possibilities. So it can be 1 or it can be P itself. But it cannot be 1. But order of H cannot be 1, as we have already proved the fact that H cannot be the a group of the singleton identity element. Therefore, the order of H must be equal to P, but that is the order of G itself. And since H is contained in G with the same order as the whole group, that obviously means H must be equal to G. So that means G is a cyclic group, right? G is a cyclic group. Since H itself was a cyclic group. Clear? There's another very useful lemma. If G is finite, if G is a finite group, then for all the elements A in G, A to the power order of G must be 1. That is identity. How can we prove this? So, if you choose an arbitrary element A from G, then you can consider the cyclic group generated by A, and it comes out to be a subgroup of G. And from here we can say that the order of A divides order of G, which we had just proved previously, right? So that means the order of G is some k times order of A, where k is some positive integer. Then what is A to the power order of G? So A to the power order of G is nothing but A to the power k times order of A, and that is A to the power order of A whole to the power k. But A to the power order of A is 1, so that's 1, right? Clear? Now we will prove a very important characterization of cyclic groups, or I should not use the term characterization, I should rather use the term a very important property of cyclic groups. Let me state this as a theorem. So if G is a cyclic group, then two specific things appear. First is G is isomorphic to Z mod nz if order of G is n, and G is isomorphic to Z if G is infinite. If G is infinite. Clear? So how do we prove this? Okay. So before moving on to the proof of this, let us first understand what the concept of isomorphism means as a mathematical topic. Okay. As a mathematical topic. So we will prove this later. Okay. So what is a homomorphism? What is a homomorphism? So let G with respect to plus, and let's say there is some G dash with respect to dot, be two groups, then F from G to G dash such that F of G1 plus G2 is equals to F of G1 dot F of G2 is called a homomorphism. It's called a homomorphism. Okay. Yeah. Now, uh, so the main thing to notice about this is that the operations are preserved under this function, right? Because see, G1 and G2 are elements from the domain, which is the group G, and G has the operation plus. So therefore, G1 and G2 are composed with the addition operation. While on the right hand side, f of G1 and f of G2 are elements from G dash, and G dash has the operation dot, right? So therefore, FG1 and FG2 are composed with the multiplicative operation, right? Okay. So if I choose any example, example number one, let's say you choose the identity mapping from any group G to a group G. So then what happens? So you have I times G is nothing but G, right? So what is I times G1, G2? So we now, conventionally we will keep on using the multiplicative operations on either side of the on either side of the mapping. Okay, we won't be using operations specifically to distinguish between the elements in the range set or elements in the domain set. We will be using the multiplicative operation as we have been as we have been using. So I of G1 G2 is nothing but G1 G2 itself, but G1 is the image of G1, right? So it's image of G1 and it's the image of G2. So it's a homomorphism, right? So it's a homomorphism. If I consider some more examples, let me find out. Okay, the next example, let's say, suppose you choose a mapping F from Z to Z mod NZ. Okay, where obviously the right hand side has the operation addition modulo n, and on the left hand side we have normal algebraic addition, right? Then if you define F from X to X plus NZ, then it's a well-defined homomorphism. In the previous lecture, we had discussed about the concepts of cosets, right? So it must be pretty obvious to you. Let's check. Let's check once. So what is f of? Okay, let me change the color. Yeah. So what is f of x1 plus x2? So this is x1 plus x2 plus nz, right? But this can be written as x1 plus nz plus x2 plus nz, right? By the operation induced on the quotient group Z mod nz. And this x1 plus nz is nothing but f of x1, and x2 plus nz is nothing but f of x2. So that's a well-defined homomorphism, right? Okay. The next is a very important terminology related to homomorphism, that is the kernel of a homomorphism. So let f from G to H be a homomorphism. Then kernel of f is the set of all those elements in G such that the image of G is nothing but the identity element. Identity element of H, obviously. So let me write it as 1H. So it's the identity element of H. Clear? And the other is the image of F. So this is the set of elements Fg such that G is in G. Clear? Now, so kernel of F is obviously a subgroup of G, and the image of F is a subgroup of H. Proving this is pretty easy, because you can notice that if you choose two elements from the kernel of F, then their images are 0, right? So what is f of G? So what is f of AB? So f of AB is equals to f of A, f of B, right? Because f is a homomorphism. So f of AB is equal to f of a and b, and f of a is 1h because it's from the kernel. This is also 1h. So 1h composed with 1h is again 1h. That means AB is also in the kernel. And the inverse is also pretty trivially noticed because we know f of a inverse is nothing but f of a whole inverse. So the inverse of the 1h is again 1h. Similarly, we can prove that the image space, or I should say the IMF, is a subgroup of H. Clear? Okay. So a very important property to notice here is that, let me write as a lemma. So a homomorphism F from G to H is 1 1 if and only if kernel of F is consisting of only the identity element. Okay. Since kernel of F is a subgroup of G, so this identity element actually represents the identity of G. So I'm not specifying it every time. Okay. Now, so suppose F is 1 1. Suppose F is 1 1. So if F is 1 1, then what happens? So then let X be an element from kernel of F, but that implies F of X equals to 0. But we know that F of 0 is also 0 by properties of homomorphism, right? And since F is 1 1, so that implies X must be equal to 0. And we typically implies that kernel of F must only be the 0 element. Clear? Conversely, let kernel of F be 0. Yeah, okay, so I'm using the wrong operation here, very sorry. So it should be 1. I should use the 1. So yeah, 1. Okay, so let this be 1. So now let f of x1 be equals to f of x2. But this implies f of x1, x2 inverse is equals to 1 by just right multiplying with f of x2 on the left hand side. But that implies x1, x2 inverse must be in kernel of f. But kernel of f is only the singleton one, right? So that means x1, x2 inverse must equal 1. And that means x1 must be equal to x2. Right? So we have proved the statement. Clear? Moreover, we also know the fact that if f is any mapping from G to H, and G and H are finite sets. Let us just speak about sets. So if they are finite sets, then f is 1 1 if and only if f is on 2. This is a very important property of functions. Okay. Let's move on to the next part. So let us talk about the first isomorphism theorem. The first isomorphism theorem. Clear? So the first isomorphism basically speaks that let f be a mapping from G to H, which is a homomorphism. Let this be a homomorphism. Okay. Then G mod kernel of f is isomorphic to the image of f. Clear? Okay. So before proving this, we must first be sure about the fact that kernel of f is a normal subgroup of G, because if it's not a normal subgroup of G, then we are not being able to define the quotient group, right? And that is also pretty easy to notice, because suppose we need to show that kernel of f is a normal subgroup of G, right? Previously we had said that any subgroup is itself contained in this set by the closure property, because any element H can be written as 1 H 1 inverse. So we just need to show the inclusion from the other side. Okay. So let say, so let G be in G. So what is the mapping phi of G K G inverse, where where K is an element, from kernel of F. Notice that phi of G, K, G inverse is basically phi of G times phi of K times phi of G inverse. But phi of K is 1 because K is from the kernel, right? So if phi of K is 1, so that is equals to phi of G times phi of G inverse, again using the homomorphism property. So this is phi of G inverse, which is equals to phi of 1 and which is equals to 1. So that means that G, K, G inverse is contained in K, where K is obviously the group kernel of phi. That obviously means that kernel of phi is a normal subgroup of G. But then this is well defined, right? Then this is well defined. So how can we prove this? So let's check the proof of this. Okay. So proof. Isomorphism is nothing but a bijective homomorphism. So isomorphism is nothing but a bijective homomorphism. A bijective homomorphism. Okay. What we do is we have G mod kernel of F isomorphic to image space of F. That is what actually we need to prove, right? So let us set a mapping phi from G mod kernel of F to image space of F such that phi of GK is mapped to F of G, where K denotes the group kernel of F. Okay, and this is a well-defined mapping, right? Because F of G is an element from image space, and F is a well-defined mapping from G to H, and GK is a well-defined element from the quotient group G mod kernel of F. Clear? So we have this mapping. So what is phi of G1K, or rather I should say what is phi of G1 G2K? So G1 G2K is basically, or rather I should not use the term directly. So what is phi of G1K G2K? Yeah. So this is phi of G1 G2K, but phi of G1 G2K is F of G1 G2, and F is a homomorphism. So this is nothing but F of G1 times F of G2. But F of G1 by definition is phi of G1K, and F of G2 is by definition phi of G2K. Therefore, this is a homomorphism, right? Therefore, phi is a homomorphism. Clear? Now we need to check whether it's 1, 1 or not. Okay. So let phi of G1K be equal to phi of G2K. But that implies F of G1 is equals to F of G2. So that implies F of G1 G2 inverse is equals to 1. So that implies G1 G2 inverse is in the kernel of F, right? Clear? No, let us not proceed like this. This won't give us much. Let's prove it in this way. Let G be an element from kernel of phi. Kernel of phi is obviously the set of all those elements from the quotient group G mod kernel of F such that it's mapped to identity. So that implies phi of G must be equal to identity. Phi of GK must be equal to identity. But phi of GK is equals to identity. The identity of the of this is FG. Yeah, so we have FG here, right? Then what is phi of GK? Phi of GK must be 1, right? Phi of GK must be 1. Is it clear? Now what do we mean by phi of GK being 1? That is the main question we need to answer. So we can think of it like this. So what is basically kernel of phi? So kernel of phi is set of those elements gk. Okay, let me commit this proof in some other. Let me drop these portions. Yeah. I don't plan these lectures, so often I get stuck. So what was written here? So yes, phi is a homomorphism. Phi is a homomorphism. So what is kernel of phi? So kernel of phi is the set of all those elements gk in G mod k such that phi of gk is equals to 1. Right? Phi of gk is equals to 1. Yeah. But this implies, so this set of all those elements G mod k such that, so phi of gk is nothing but f of k is equals to 1. So therefore gk such that G mod k such that, so f of k is, f of g is equals to 1. So f of g equals to 1 means g is in the kernel. But if G is in the but if G is itself in K, then what are the elements GK? Then is the whole subgroup K, right? So this is equal to K. And K is the identity. K is the identity of the quotient group G mod K. So kernel of phi is identity. So that means phi is a 1-1 map. The phi is a 1-1 map. Clear? Onto is pretty trivial from the definition of the function, right? Because for all fg in image space of G, there exists some G in, or I can say some G in G such that Gk belongs to G mod K with Gk map is being mapped to Fg. Right? So this it's on. So every image has a pre-image Gk, right? So it's an onto function. So it's a 1-1 mapping, it's an onto mapping, it's a homomorphism, therefore it's a homomorphism. Therefore G mod kernel of phi is isomorphic to the image space of phi. Clear? Clear? Now let us come to the properties of cyclic groups which we are talking about. Yeah, so this one. So now we will try to prove this. Proof. So we prove the first part. So let order of G be equal to n. Okay. One second. One second. One second. Okay. So yeah. So order of G is equal to n. Okay. Now, what is the order of Z mod nz? Okay. What is the order of Z mod? So we know that it is the set of elements 0 bar to n minus 1 bar. So it's obviously n, right? So both are finite dimensional with the same number of elements, right? So if I consider a mapping from this to this, okay, and we prove that mapping to be 1 1, then it suffices to say it's 1 1, right? Yeah. So um, now what are the elements in G? So let G be generated by A. Let G be generated by A and define a mapping phi from, let's say, G to Z mod nz such that phi of A to the power I is equals to I. Now this mapping is obviously well defined, right? Because we had just studied the structure of cyclic groups and we have shown that the exponents are nothing but the residue classes of the integers in Z mod nz, right? So it's well defined. Now, is it a homomorphism? So phi of AI1, AI2 is nothing but phi of AI1 plus I2. So this is equals to I1 plus I2. And what is I1? I1 is phi of AI1 and this is phi of AI2. Right? So on the right hand side we obviously has the plus operation modulo n. You can use modulo n, but it's actually not required, right? You don't require the modulo n here because it's obvious on the left hand side when you are having a to the power I1 plus I2, that's here modulo n is already induced. Right? So you don't need to actually mention the concepts of modulo n. So it's a homomorphism typically speaking. Now what can we say about one oneness? What is kernel of phi? So kernel of phi is the set of all those elements a to the power I in G such that phi of a to the power I is equals to 0, right? But phi of a to the power I is equals to 0, this means I is equals to 0 itself, right? It means I equals to 0. So if I is equals to 0, then kernel of phi is the singleton set 0. Therefore phi is 1 1. Now we have already checked that the cardinality of G and Z mod nz are same, so 1 1 implies onto. Therefore phi is an isomorphism. Therefore phi is an isomorphism. Clear? Let's prove the other part. So let again phi be a mapping from Z to G, where G is again generated by A, but is an infinite group, and is infinite. Such that, so we map an element n from Z to A to the power. So this is obviously homomorphism by the properties of exponent. There's nothing to prove there. Ontoness holds trivially by definition of phi, because any element a and you take from G, there is some element n in Z such that n is mapped to A to the power n. So onto is trivially holding in ontoness is trivially holding in case of phi. Is it 1 1? Suppose phi of n1 is equals to phi of n2, then that would imply a to the power n1 is equals to a to the power n2. Then that would imply a to the power n1 minus n2 is equals to 1. Now the problem is if n1 is not equals to n2, then there exists some r in natural numbers such that r can be written as n1 minus n2. And to say this, we assume that n1 is greater than n2, which can obviously be assumed without loss of generality, right? But that implies a to the power r is equals to 1, but that implies the order of a is finite. And that would eventually imply that the order of G is finite as well, right? Because G is generated by A, and A has a finite order. But therefore a contradiction, because we have chosen G to be infinite. Therefore n1 must be equal to n2, and which implies phi is 1 1. Right? So phi is 1 1, phi is onto, and phi is a homomorphism. Therefore G is isomorphic to Z. Now one important property to notice here is that in the proof part 1, we chose the function from Z mod nz to G. In this case, we chose the function from G to Z. And in both cases, we establish an isomorphism. Now, what is the meaning of an isomorphism? So, in the previous lecture, I had said that isomorphism in very literal sense means that the group structures are same. Though they have different elements, but their group properties and their group structures are same. Right? For example, if I say, so suppose if G is cyclic, what happens? Suppose if G is abelian, what happens? Suppose if G is abelian, what happens? What can we say about the homomorphic image of G? Or the isomorphic image of G, whatever you want to say. 1 second. Huh? So what I mean to say is, suppose G is abelian. Then what about phi of G? Where phi is a homomorphism. Where phi is a homomorphism. So if G is abelian, then for all G1, G2 in G, G1, G2 equals G2, G1, right? But that implies phi of G1, G2 must be equals to phi of G2, G1, because to ask a question about a homomorphism, the homomorphism must at least be well defined. But that means phi of G1, phi of G2 must be equals to phi of G2, phi of G1, right? And G1 and G2 are arbitrary elements. So phi G1, phi G2 are arbitrary elements from phi G, right? So that means phi G is abelian as well. That means phi G is abelian as well, right? The thing is that if I talk about an isomorphism, then we can establish an equivalence relation out of isomorphisms. Okay. What I mean to say is, let G1, G2 be two groups, or I should say it like this. Let G bar be the collection of all groups. Define a relation, say this, on G bar such that any G1 is related to G2 if and only if G1 is isomorphic to G2. Clear? Now we claim phi is an equivalence relation. Phi is an equivalence relation. And this claim is very easy to prove. Why? Because I'm just giving the hint to it. See, you can choose an identity mapping from a group to itself, right? And this will come out to be a well-defined bijective homomorphism. So that would imply that G is isomorphic to itself. Then if F is a bijective homomorphism from G to H, then that would imply F inverse is a bijective homomorphism from H to G. If F is a homomorphism and if F inverse exists, then F inverse is also a homomorphism. That's very easy to prove. So that instead means H is related to G, right? And again, if F from G to H is a bijective homomorphism and G from capital G to, sorry, from H to some Z, let's say, is another homomorphism, then G composed with F, so it is a mapping from G to Z, is again a homomorphism and bijective as well. So that means G related to H related to Z implies G related to Z. So it's transitive as well, right? So G of F is obviously homomorphism because see G of F, what is G of F of G1, G2? Or let's say alpha 1, alpha 2. So this G of F of alpha 1, alpha 2. So that's G of F alpha 1, F alpha 2. That is equal to G of f alpha 1 times g of f alpha 2, and this is nothing but g of f of alpha 1, this is g of f of alpha 2. That's very easy. So this means that isomorphism can be considered from both sides, right? So that basically means that if you consider so basically G isomorphic to H is same as H being isomorphic to G, right? So that is why in the first case we proved that Z mod NZ is isomorphic to G, and next we prove G is isomorphic to Z, because they actually has nothing to do with in which order we are writing the groups. Clear? The ultimate sense is that both of them are having same group structure. Clear? Okay. The next topic we want to discuss is the topic of group actions. Group actions. I'll try to be, as detailed as I can. At the same time, I will obviously try to be very simple. Okay. Because often the topic group action becomes very rigorous to understand. But I'll try to be as simple as I can. Clear? Okay. So a group action is basically imposing a group on an arbitrary set. Okay. Or you can think of it as we are trying to impose something, or we are trying to restrict the elements of an arbitrary set A using elements of a group. Okay. Okay, let us start with an example. Suppose you consider the set Sn. Okay, so Sn is basically the set of all permutations of the first n integers. You can consider of it like that. Let A be the set of first n integers. Then Sn acting on A, this in very literal sense means, so this means we permute the elements in A using each permutation from Sn, right? That is, suppose you have A to be like this 1 2 3 4, let's say, and you choose the permutation 1 2 from Sn. So 1 2 when is acting on this, so it's causing a permutation in A. So elements in A get oriented in the form, say the 1 goes to 2, right? So it's 2 here, and 2 goes to 1, so it's 1 here. Yeah. So this sort of an idea is what group actions actually impose. Yeah. So let us come to the definition. Okay. So a group action of a group G on a non-empty set A, denoted as G acts on A. So it's a mapping. We denote this mapping as O, or you can think of it as the composition symbol as well, from G cross A to A, such that the following properties hold. So what are the properties? The first property is that G1, G2 composed with an element small a is same as G1 composed with G2 composed for all G1, G2 in G and small a in capital. Okay, because see, G2 composed with A, so this is an element of capital A. So G1 must be composed with A. We cannot just arbitrarily multiply G1 and G2 in the sense that G is a multiplicative group. Here the multiplication is defined because G1 and G2 both are elements from the group G, right? And the second property is that 1 composed with A is A. But 1 is obviously the identity element of G, because we are considering G to be multiplicative. Is it clear? So if this happens, we consider G to be, so we consider this to be an action of G on A. Clear? Now notice certain things. So if G acts on A by composition, so if G acts on A, then we can fix A. Suppose we fix A. Okay. Then let A in A be fixed. Let sigma G be a mapping from A to A such that sigma G actually maps A to G composed. So G acts on A, that means G composed A is well defined. Clear? But now notice the fact that this mapping is obviously well defined, right? Because we are choosing an element from A and G composed is also an element in A. But the thing is that you are choosing an element from A and you are sending it to some other element of A or to itself only. So sigma G, so what I actually mean to say is that isn't sigma G a permutation on A? Because actually if you iterate through the elements of A, if you iterate through the elements of A, then sigma G rearranges the elements. So it rearranges A, right? So for example, let's say A is 1, 2, 3, 4. So suppose sigma G sends 1 to 2, sigma G sends 2 to 3, sigma G sends 3 to 1, and sigma G sends 4 to 4. So what does sigma G do on A? So it actually rearranges these elements as 2, 3, 1, 4. So sigma G basically acts as a permutation on the set A, right? So if it acts as a permutation on the set A, then sigma G must be in the set SA, right? SA is the set of all permutations on the set A. Okay. Therefore, let F be a mapping from let's say G to SA such that every element G is mapped to sigma G. This comes out to be a homomorphism. Clear? This comes out to be a homomorphism. Got it? Clear? So suppose this mapping is, yeah, so we have written it as F, right? This F is basically called the permutation representation. The permutation representation associated with the action of G on. Clear? Okay, so it's already a 53 minutes long lecture. So let this lecture be up till this much, guys. In the next lecture, we will be exploring the concepts of group actions. So meet you guys in the next lecture.